Again, item B, intrinsic geometry, exterior algebra, extend to R3 and R4. Now B part 3, miscellaneous topics, intrinsic geometry extended to extrinsic geometry. Now, this is B part 3, lecture 3A, application of Lie bracket, Euler Lagrange Equations. You see, let's emphasize. You see, Lie bracket. This from the Euler Lagrange Equations. Just we use Legendre identity, and then to relate Hamiltonian to Lagrange. And Hamiltonian can be expressed in using the Lie bracket. Okay, that's our goal. So, from Newton's second law, a particle of mass m in R3 under a force F is equal m, the acceleration. This is a vector, the function of position vector, velocity, and time. If the force is conservative, what is conservative? You see, the force can be expressed as a gradient of a scalar. Why? Gradient of phi dot dr, this is a vector, is the phi, which is phi at b minus phi at a. So the trajectory does not depend on the way I'm traveling. You see, just the end minus the initial. The phi is a function. So if it's a conservative, there exists a potential energy function V, such that F is minus gradient of V. You see, V here is a function. Attention now. You see, it's important, this minus sign, because when the potential decreases, the kinetic energy increases. Okay? Just why I set minus over here. Then, from the Newton's second law, I substitute F by minus gradient of this function, okay? With the function of position and time. 1. The actual functional S is defined as S depends on the path, okay? Is the integral T1, T2. This is the Lagrangian, okay? Qi, the velocity and time, where L is the Lagrangian and Qi is the generalized coordinates. The principle of stationary action says del S is equal 0 by definition. Now, we want to find the form of L and show that the variational of S is 0. And I'm sorry, this will find the Lagrangian, how it relates to the kinetic energy and the potential. That's objective here. So, and these two generalized coordinates that are the vector, position vector, is a function of this case, or these coordinates here, generalized coordinates, and t. And the velocity, r dot, is just to derive it's quite easy, you see. This is the velocity here, and this is what I call transient part, and this is called a transportation, okay? This is transport, this is the accumulation, as you see ahead. I is dummy indices. So the kinetic energy is defined as T1/2 m, the dot product between the vector velocity, and this is T function of the generalized coordinates, generalized velocity, and in this case, and t here. T. Now, the potential energy is a function v, okay, depends on the generalized coordinate and the time. Thus, define the Lagrangian L. You see, let's put T over here. As L is defined as the kinetic energy here minus the potential energy. Now, the principle of stationary action. You see, let Qi be the path from which delta S is equal to 0 under variations. Qi is Qi plus delta Qi. See, this is for Taylor series with delta Qi is delta Qi T1 is delta Qi T is equal to 0. So this is the extreme T1 and T2. I impose this. See, I have to impose. Then delta S, the integral of delta L. Don't forget that the delta L is over here. You see, this is L over here. I will apply delta on the left-hand side and delta on the right-hand side. And then I expand. You see, this is a derivative. Okay? So this plus this, delta T. Now, this delta S now will set this, we'll derive this integral here using integration by part, as you see on the lecture 3b. You see? Now continue this. Okay?